In chapter 6.2, we will be talking about revolutions, where any area is rotated about the x-axis, y-axis, or any other line on the plane to make a solid with the volume, as shown here. In order to find the volume, we must understand that, like when we learned about finding the area under a curve, we can split the solid into separate pieces in order to find an estimate. When we were looking for the area, we divided the space using rectangles. We can also divide the solid up using cylinders. Like area, the smaller each division, the more accurate our answer will be. In order to find the volume of each cylinder, we must remember the formula, pi squared times height. From the picture we can see that the radius corresponds directly with the y value, which will be given in the function. In addition, we can see that the height of the cylinder is just the x values through which the cylinder passes. Therefore, we can rewrite the equation with respect to the function so that it looks like this. Pi times f of x squared times the change in x. But we must remember that the functions are almost never a perfectly straight line with a single y value. And so we want to divide the volume into as many intervals as possible to get the most accurate answer. By using Riemann sums, we can write the equation for the volume to look like this. And with our knowledge of integrals, we see that this is equal to this. The integral from a to b of a of x dx, where b minus a is the change of x, and a of x is pi times f of x squared. In other terms, we can understand this formula to mean pi times the integral from a to b of the radius squared dx. Sometimes the area that is being revolved is captured by two functions. So that the center of the solid is hollow. We can expand the previous formula a little so that it looks like this. Pi times the integral from a to b of the outer radius squared minus the inner radius squared dx. All this means is that we are finding the volume of the bigger cylinders and removing the smaller cylinders on the inside. So the first problem is rotate the region bounded by y equals root x, y equals 3, x equals 0 about the y-axis. So first we want to sketch out what the problem is asking for. So we have x equals 0, y equals 3, y equals root x. And when you rotate about the y-axis, you'll get something that looks like this. And first we want to identify what the radius is, and it's going to be y equals root x. But because we're rotating about the y-axis, we want to write it in terms of y, so x equals y squared. Now we can write the equation for the volume. So we have the integral from 0 to 3 of pi times y squared, which is the radius, squared dy. You can bring out the pi because it's a constant. And you find the antiderivative. Get this. And then you use the fundamental theorem of calculus and you get pi over 5 times 3 to the 5th minus 0. And your final answer will be 243 over 5 pi. So our next problem is rotate the region bounded by y equals 2x squared and y equals x cubed about the x-axis. So again, we want to sketch out the problem first. We have y equals 2x squared and y equals x cubed. And this is the region that's bounded. And when you rotate about the x-axis, you'll get something that looks like this. And take note that it's hollow on the inside. And so we have to find the intersection points. So you set the functions equal to each other, and you get x cubed equals 2x squared. You bring this to the left side, and you factor, and you get x equals 0 and 2. The coordinate points are 0, 0, and 2, 8. Then we have to identify what the radius are. The inner radius is going to be x cubed. It's closer to the x-axis. And the outer radius is 2x squared. Now that we identified the radius, we can write the equation for the volume. So we have the integral from 0 to 2, as we found in the intersection points, 0 to 2, of pi times the outer radius, 2x squared, minus the inner radius squared, which is x cubed. And you bring out the pi because it's a constant. Simplify. And you find the antiderivative. Using the fundamental theorem of calculus, you get the final answer of 256 over 35 times pi.